second presentation, which is the grid-aware distributed control of electric vehicle charging stations in active distribution grids. And it will be delivered by Sherif Fahmy, who was born in Egypt. Sherif carried out BSc and Master's studies at the École Polytechnique Fédérale de Lausanne in Switzerland, where he specialized in smart grids. He started a PhD in 2017 in the Distributed Electrical System Laboratory at EPFL, headed by Professor Mario Paolone. His thesis focuses on the real-time control of unbalanced and uncertain active distribution networks. Please, Sherif, start your presentation.
Thank you very much, Professor Acha. Let me share my screen. So here we go. I hope you can see. Is everything okay? Yeah, perfect. So yes, I'm Sherif. Thank you, Professor Acha, for the presentation. Together with Mr. Rahul Gupta and Professor Mario Paolone, we submitted this paper, and I'm here to give you a brief overview about the paper so that you can read it nicely. So let's dive right into it. Distributed renewable generation and the electrification of public transport have been prompted as potential solutions to reduce CO2 emissions. There are problems when thinking about the fact that electric vehicles are penetrating power distribution grids. Namely, they have high power demand, which implies that they might have higher risk to violate distribution grid constraints, namely ampacity limits, under voltages, substation transformer overloads. Another issue is, or another impact is the high penetration of single phase EV chargers. And this creates unbalances which deteriorates the power quality, which this led to this general problem statement, which is to developing an electric vehicle power allocation algorithm accounting for EV user needs, grids operational and power quality constraints, and the stochastic nature of power generation and non-EV loads. Now, this has been studied in the literature. The typical issues that we can face when tackling this problem are, for instance, the stochasticity of EV user behaviors. In our case, we mitigated this by using directly inputs coming from EV users. Another one is the stochasticity of distributed generation. The solution is that we went for scenario-based optimization based on historical data. Another issue is the non-synchronism of EP peak loads and demands with respect to the DG. For that, we do real-time optimization. The scalability of centralized control we propose through a centralized problem that actually is distributed. So a distributed problem using the ADMM method, alternating direction method of multipliers. And finally, the big issue is to usually integrate the power constraints or power quality or operational constraints. We leverage a three-phase linearization of the generic power flow equation. Now, a general idea of the problem formulation. The problem formulation can be basically divided into two: a grid subproblem and an EV subproblem. The grid subproblem is a stochastic optimization to maintain the grid in a feasible state, and the EV subproblem is a deterministic problem that decides how much power each car should have in order to reach a target state of charge. Now, they have inputs, objective constraints, and outputs, and I will go through them right away. For the grid problem, the inputs are the nodal power injection scenarios and grid parameters. Now, what is a scenario for us? A scenario is basically a collection of nodal apparent power injections for all resource nodes, excluding the EV injection. Now, they are basically sampled from probability distribution functions. These PDFs are pre-computed, so they are computed pre-optimization using historical yearly power profiles. So first, the profiles are clustered. Once they're clustered, each subcluster is basically fitted with a multivariate Gaussian mixture model in order to account for time correlation. The second input of our problem are grid parameters. Grid parameters are namely the branch parameters, the three-phase pi model circuit equivalents, and where are the resources. So these are the inputs of the first grid subproblem. The second dimension are the constraints. The constraints, or the hard constraints of the problem, are directly the grid operational and power quality constraints. So these are the phase to neutral nodal voltages per phase, 3-phase, the branch currents per phase, the slack apparent power, and the negative, positive, and zero sequence phase to neutral voltages. They're all in magnitude and they should be within bounds. These are the constraints of our problem. Now there's a superscript D because this has to be verified for every scenario. Then we have the inherent problem, which is this is non-convex, so we need to linearize it. The linearization that we chose is a first order Taylor expansion. It has 3 dimensions. The first one is the state around which we are, or the quantity around which the first order Taylor expansion is made. The second one is what we call sensitivity coefficients, which are partial derivatives. And the third dimension are actually our control variables, which are the increments. So T here is the time step of the algorithm, and PTEV and QTEV are the optimization variables of the problem. They are the per node EV injections per phase in the grid. Moving on, maybe a small detail here. You can see that there's no superscript T here. This is because we want our constraints, our variables, to verify these constraints for all scenarios. So moving on to the objective here could have been anything for the grid subproblem. So we just chose to minimize the per unit ampacity, branch flows, using only the reactive power. I can comment on that in the questions if anybody has a question about that. And the outputs are therefore the active and reactive power injections aggregated at a node level of the EV injections. Now, moving on to the subproblem of EV, the inputs are the car model. This gives us a detail about what is the maximum charging power, the battery capacity, and the charging efficiency. This specified departure time, so the user has to tell us when he's leaving, the initial state of charge, the target state of charge, or the target charge as at stopping time, and then another variable which is called tau plus. This is a Boolean that explains whether or not the algorithm should continue charging the car in case the user does not leave at the specified departure time, but after, and the state of charge target has not still been reached. So for the constraints, there are 3 main constraints. The power modes. So basically here, the algorithm supports whether it's AC monophase charging, AC single phase, AC 3-phase charging, or DC charging. DC charging here is modeled as a symmetrical AC 3-phase. The second constraints are the power limitations. So the power limitations of the converters or the car, or the maximum charging powers of the cars. The third is that the state of charge should not ever exceed the target one. The state of charge in our problem, we consider that it might be measured, but it also can be estimated. If it's measured, it's sent by the car. If it's estimated, it's computed using simple Coulomb counting method. And finally, the link to the grid subproblem that I have shown you before. So these are the per phase, per EV charging station. K is the EV charging station, I is the node of the grid, T is the time step, and the per phase active and reactive power that are given by the car, that are linked to the aggregated nodal injections in the grid. For the objective, we have 2. The first is to fairly achieve the target state of charge. Namely, here it's to minimize the difference between the target state of charge and the one in the next iteration given by this. This fairness is achieved through kappa. So kappa, what it tries to do is that it tries to weigh, depending on the car, the different objectives in order to give more importance to cars that have less time left before their specified departure time and a lot of energy needs still left. So this basically boils down to 4 situations. If the omega is whether or not the car is connected. So if it's not connected, then nothing has to happen. If it is connected, but the tau is whether or not we surpassed the preset departure time. If it's surpassed, but we did not ask to charge after that, then it's 0. And in the 2 other cases, basically, it is a weighing factor to take into account the remaining time and the remaining state of charge. The second objective is to minimize battery wearing. So this, in our problem, we do through trying to minimize subsequent active power variations in the charging power. This is done through also another factor, which is lambda. Lambda here takes into account the history of when starting from the point where the car has been connected until now, whether or not the powers have varied or not. If they varied a lot, then this lambda increases, which means that the weighting has more weight, and more weight implies that we have more penalty. Now, the interesting thing about this is that all these weights can be directly applied because the nature of the objectives are all the same. They're all in percentage. That's something that was worth noting. So finally, the centralized full optimization problem has a scheme like this, where we have one grid subproblem that's taking care of the grid and the grid constraints, and EV subproblems that are taking care of the charging demand needs. Each EV subproblem can be in practice solved at an EV aggregator level, which is basically the EV aggregator at the point of each node that has charging stations in the grid. This is from construction linear and separable, which comes to the next slide directly, because the unfortunate thing about this centralized full optimization problem is that it's not scalable and it requires sensitive EV user information to be shared. Therefore, we realize that just by construction, if we repeat the optimization variable of the grid constraints, so these per phase nodal injections, aggregated nodal injections, we obtain a shareable problem and a standard sharing problem that can be solved using algorithm 1. So algorithm 1 is using the iterative scaled ADMM framework to solve the problem. It's solved by first, at every EV aggregator level, local problem is solved and the solution in parallel, and that solution is sent to a centralized grid aggregator that solves only the grid subproblem, but accounting for the other solutions coming from all the other EV aggregators, and it updates the dual variable, and then it checks convergence. What is convergence? Is simply here verifying whether the solution of the grid aggregator problem is within bounds with the individual solutions that were sent by the EV aggregator problem. So yeah, coming now to the results. The idea was that we wanted to illustrate the how our method behaved. So we did a comparative simulation of 3 EV controllers for a 24-hour summer weekday. This summer weekday pertains to the scenario generation with a control time resolution of 5 minutes. So the 3 controllers are the one we developed. We called the grid-aware distributed controller. Another one, which is the grid-unaware local controller. This one is just solving the local EV subproblems without having any knowledge of the grid. And the third one that is called the myopic maximum power controller. This is simply a controller where whenever an EV is plugged, it charges it at maximum power until it reaches state of charge or it is unplugged. It's interesting to note that in this case, the GOLC and the MMPC have no reactive power because there's no reactive power control. It's only purely active power. And just to give you an idea about what happens at every time step. So at every time step, we first sample the scenarios that the GADC needs. We use the same EV user data and we give it to the 3 controllers. The 3 controllers then output optimal EV injections. At that point, for every controller, we perform Monte Carlo load flow simulations. So in this case, we use samples from the PDFs that were already originally generated, but a lot more samples of the non-EV injection nodal injections. Sorry, we give the same scenarios to the Monte Carlo load flow simulation for each of the controller, and we compute, and it outputs the probability distribution functions of the grid variables actually. So coming back to the comparative simulation again, the grid model that we used was, we used the IEEE 34 feeder without regulators. These scenarios were generated using real measurements actually. So what you see in figure 2 are the aggregated PV, in this case photovoltaic, because we consider generation as PV, and loads for at this slack level. So this is the sum over all the 3 phases at the slack level that is already clustered into a summer weekday. So what we do is that these are the curves that are directly used to generate our GMM models. To get reactive power from the active power, we use a random, we randomly take a number between these power factors. So here are the nodes and the node placement where we have generation and the maximum powers. And to get the per phase, we actually randomly distribute per phase with a 20% maximum difference in unbalances. Yes, moving on to the EV model. So something interesting here for this simulation is that the EV model, the EV user behavior was completely synthesized. So in our work, we categorized EV chargers into 3 types: home, work side, home, work, and roadside. The home, and based on that, each of them had different behaviors, different amounts of charging stations connected to a node, different charging modes, etc., etc. You can have more details about this in the paper. I just wanted to show you directly the results. So here we show the post Monte Carlo load flow simulations, the probability to violate the grid operational constraints. So as you can see, the GADC has no violations, but sometimes due to linearizations, we have a little bit of violation here. Both, you can see that it's in this simulation, most of the problems happen at night, where we have a lot of violations for both the grid unaware controllers. A similar, sorry, Enrique? Yeah. Oh, okay. A similar behavior is happening with the power quality constraints, where we have also at night a lot of problems. This is probably due to the fact that we have a lot of single phase chargers at night that are connected.
Sherif, excuse me, 2
yes.
minutes left.
Yes, thank you very much. The conclusion is coming right away. Thank you very much, Enrique. And so maybe just to tell you also something else that's interesting about the results, the probabilities actually to violate the constraints are a little bit less when it comes to the grid unaware local controller compared to the myopic controller, because we have this smoothing effect in the objective of the local controllers to protect the battery. Now, from the EV side perspective, so we saw that the grid had issues. From the EV side perspective, obviously the myopic controller has the best behavior. What you see here are a block spot representation of the difference between the target state of charge and the acquired one at the end of the departure of each vehicle. So the MMPC is the base case because it's charging at full power, and you can still see that there are values that are non-zero. This is simply because we randomly chose the initial and target state of charge, so we have situations where we just don't have enough time. The local controllers behave very similarly, and our method behaves similarly as well. However, you can see here that during nighttime charging, because nighttime charging was really for home chargers, you can see that they have more, they do not, let's say, reach EV user needs more than the myopic controller, and this is normal because it was protecting the grid. So as a conclusion, I just wanted to say that a grid-aware distributed controller for EV charging stations was developed in this paper. We use ADMM to distribute a separable formulation into local problems solved at EV aggregator levels and a grid aggregator problem. Power flow linearizations were used, and like this, we accounted for grid operational and power quality constraints directly in the problem, which is something that was novel. The performance showed that the grid unaware local controllers obviously satisfy better the EV user needs. However, when it comes to the grid, it can create a lot of problems in the illustrative simulation that we showed. And finally, that we believe that a method like this that is really axed towards the grid can be used by grid operators actually to control weak grids that have high EV penetration. Thank you very much, and I apologize for the delay.
Thank you very much, Sherif, for a very, very good, interesting presentation, very clear, being a complex topic. We have one question waiting for you in the Q&A session. If you could answer very quickly, that would be most appreciated.
Yes, I can read it out loud. So when you derive the first order Taylor expansion to linearize the non-convex problem, what is the operating point you derive this, i.e. the PQ states? Yes, so I think I understood this. Thank you very much for your question, Tao. So the point that we start from is the scenario plus the EV injections from the previous time step that are optimal. So this is done so that the increments, if I can go back, I think my screen is still shared. If I can show you very quickly here, yes. this is because we wanted the increments to be as small as possible. So we're doing t minus t-1. So these injections are the scenarios that we generate plus the t-1 optimal injections of the EVs.
Excellent, excellent, Sherif. I think the question has been answered very comprehensively. Thank you very much for presentation, your response to questions.